This is yours as well. I mean, that was from my
thing for a while. Tell you what, unfortunately, I'll do them on the board, but you're gonna have to tell me the information will work through. Literally, I created this by just taking a look at your homework and modifying it. And it was extremely, I think it was very straightforward, but the biggest mistake, I think, was not having a clear understanding of what the formulas meant. Have you all been able to see the solutions on OneNote? You can. So if you have any questions about how I got to it, you should be able to. And on the third one, the last part, everybody got full credit for that. So with that in mind, we'll just go through them. So problem one, can you just give me the specifics? Give me the first thing, because I don't remember that.
2 centimeter long, short dipole, unknown current, oriented in the Z direction, at range 4,000 meters, angle 45 degrees. The power density is PAV equal to 30 microwatts per meter squared.
So here we're given PAV equals 30 microwatts per meter squared. And the frequency was, I think, 10 to the 8th hertz, right?
Frequency is not given.
It's at the bottom.
It's a
Oh, yeah, it's in the second part. Yeah, 100
all right,
megahertz.
so right off the bat, I can say the wavelength is C over F, or 3 times 10 to the 8th meters per second over 10 to the 8th, or 3 meters, and therefore L over lambda is much less than 1. It's a short dipole. It was stated it's a short dipole, right?
Yeah.
All right, now if it's a short dipole, the next thing you know is the gain itself will be 1.5 times the sine squared of theta. For all short dipoles or small dipoles, that's understood. Anyway, the first part, I think they asked for both E and H, right, at the point of observation of the field, right? In other words, out here at a range of 4,000 meters, right? Correct, class, everybody? Now, most of you got this right. So once I'm here, I just go methodically through it. I know the average power density is equal to 1/2 times magnitude of E squared over eta naught. And eta naught, I know because it says free space is 120 pi ohms. And therefore, I can say the magnitude of E is just equal to the square root of 2 eta naught right here times P F. Now, you can do the math on this, but it's straightforward. There's nothing tricky about this. And when you do it, I want to say it's 0.15 volts per meter. You can check me on that. Anybody confirm that?
Yeah.
All right, so that's just plug and chug. Now to get H, because you're out there, 2 ways to get it. You could say it's equal to 1/2 times eta naught times 8 squared and solve it this way. Or you could just take E and divide it by eta naught. Either one gives you the same exact answer. So if you take E over eta naught, you'll get it. And this one I don't have committed to memory. What is that? That's right. 4 times 10 to the minus 4th, and this would be amps per meter, or really 0.4 milliamps per meter, right? These are straightforward, correct, class? Just checking boxes. There's nothing tricky about Now after that, I want to say total radiated power, is that the next?
Yeah.
All right,
Ready?
so there's about 4 or 5 different ways you can get this. It doesn't matter how you get it. Because you can get the E field from a short dipole, you know what that is, you can figure the current from that. You can do all sorts of stuff. Here's the way I'm gonna do it. And I think I did this in the solutions. I know that the power density out here, if it's a short dipole, average power density is equal to total power over 4 pi r squared. That's the isotropic. And then you multiply it by the gain, which is 3/2 or 1.5 times sine squared of theta. That's just checking boxes to get total power, right? Correct, class? This is nothing tricky if you look. All right, now I want total power. So the only thing, I know that this, the sine itself is the sine of 45 degrees, right? Sine of 45 degrees is going to be 1 over square root of 2 squared. It's going to be 1/2. So I can go further and say this is really going to be equal to total power, right, times 1/2 times 3/2, and I'm just putting it out here, over 4 pi, right, and then R is 4,000, right? 4,000 squared. I can go ahead and just inverse solve this thing, and since P average there was 30 microwatts, I can get P total here equal to P ab, which would be equal to 30 times 10 to the minus 6. Then it's going to be times 4 pi times 4,000 squared, and then it's divided by 3/4. And when all is said and done, you turn the crank. What was that? It's 10 to the minus 6 something. Total power. I mean, it's not 10 to the minus 6, sorry, 8,000 something.
I got 8,068.
That's right. You can check it. 8,006. 608, I'm not even sure, but you can check on that. And that's going to be watts. So that's total power. And again, just doing it in inverse, but there's many ways to get this. There's so many different ways. You could get the electric field from a short dipole is J eta beta I L over 4 pi R times the sine of theta, and you could get I from that, and I put the radiation resistance there, right? So it doesn't matter which way you use, you could use that as a confirmation method just to make sure you got the right value. Once you have the total power transfer, I think they wanted I, right? Now you need the radiation resistance, and I'll put it over here. For this one, R rad was equal to 80 pi squared, and it's L over lambda squared. And you're going to need this. So this, oh, I wish I remembered this. Anyway, it's going to be 80 pi squared, and L is 2 centimeters, so it's 0.02 over wavelength is equal to 3 meters. And you're going to get a value for that. We'll get to that in a second. And then you can say total power transmitted is 1/2 times R radiation here times I squared. And therefore you can say that I itself would be the square root of 2 times P transmitted, total power transmitted, or P radiated, divided by R rad. And what was R rad? I'm sorry, the answers are up on OneNote, I just don't remember.
R rad or P rad?
But the radiation resistance, because you're going to need that. Isn't it?
It doesn't have R rad calculated formal solutions or solutions.
Wait, the value or the equation? Oh, you have the equation.
Yeah, I just need the value. Just take 0.02 over 3 and square it times 80 pi squared. It's around and on, something like that. I forgot exactly. Anyone? It's not on the solutions? I'll put it in there. Anybody?
Sorry, is it just a calculator?
Huh?
Had to adjust the calculator to back to radians.
Ready? I mean, this should just be straightforward. 0.02 over 3 squared times 80.
0.0351.
I'm sorry, you're right, 51 ohms. Now, once you have that, stick that into this equation. That's 2 times 80, or 8,608, I guess, divided by that, and take the square root, and you're going to get I. Exactly what that is, 667, something like that?
I got 678.
678?
So,
All right. And then what else is asked for in this one? Is that it?
the average, it says P average if the angle is 90.
Oh, yeah. All right. And you can do this a couple ways. You know the power here, if you think about it, we got total transmitted power, right? We know that there was a factor of 1/2 that entered in here, right? When sine is 45 degrees, that's 1 over square root of 2 squared. So you know, really, the power is going to be bumped up by a factor of 2 there. You didn't even have to do a calculation. Or you can just do the calculation for the last part when they want the average power right here. And they want this at R equals 4,000, right? Theta equals 90 degrees. Well, the sine of 90 is 1, and therefore this is just equal to total transmitted power over 4 pi R squared, and here it's 3/2. It will be twice the actual power at 45 degrees, or it's going to be 60 microwatts per meter squared if you look, right? And that was the first problem. It's entire. I literally took a homework problem and then modified just the range, I think, and that was it. And I didn't give you the current here. I gave you the value of the power density, and you had to do the inverse problem. That happens a lot. Okay. Problem 2. Were there any questions about this? By the way, I think this, today we're supposed to get rain later. I'm not sure how late, but from that tropical storm's outflow. So for problem 2, can you go ahead and just give me the specs on it?
Assuming plane wave propagation in free space,
Oh, yeah, I give you E equals, go ahead.
20 e raised to the negative j50z, and that's x direction,
AX, yeah.
x. And then you need to find h and frequency and direction of propagation.
H, F, and AP, direction propagation. All right, for these are just box checkers to make sure you know that what this terminology means, because some people actually don't. If you look at this right off the bat, that's beta. So beta is equal to 50. Everybody should be able to do that without even a hesitation. It's the coefficient of the range propagation times J, right? The direction it's moving, I look here, I know it has a coefficient of Z, so it's in one of the Z directions, right? Because it's minus J times the coefficient beta, I know it's moving in the plus Z direction. Y'all follow me on that? Now, people made mistakes on this. They put it in the minus Z. That minus sign indicates it's going in the plus Z direction, so that means this is AZ. Finally, for the H field, the only thing I cared about was the magnitude. Somewhere in there it says it's in free space, right? Or in air. Y'all follow me?
Yes.
And eta naught is 120 pi for air, and therefore H is just magnitude of E over eta naught. I want to say it's 0.057 amps per meter. You check me on that. Is that right?
0.053.
0.053, sorry. So H is equal to 0.053. Amps per meter. And the frequency, there's several ways you can get frequency. Well, beta is equal to omega times square root of mu epsilon. This is one way. I'm just showing you. Well, when I look at that, that means 50 is equal to 2 pi f. Square root of mu epsilon in free space is c, right? 1 over c. So it's divided by c, correct? And that means f itself is just going to be 50c over 2 pi. Do y'all agree with this? We could get wavelength first if you want. I know that beta, right? Beta times wavelength is 2 pi. You could do this and then wavelength is c over f. It doesn't matter which way you go. It's going to come down to the same answer. So the frequency on this one is
2.4 gigahertz.
pardon?
2.4 gigahertz.
2.4 gigahertz. All right, that was straightforward. The second one I had a correction on, and I gave you h is equal to, give me the value first.
H goes 10.
10
E to J 30.
e to the j 30 z and the a.
AY.
Right. Thankfully, this didn't actually affect the problem, because that's just orientation. So the first thing I wanted to find out was E, right? Well, E will just be eta naught times the magnitude of H. H right here, right, class? And when you do this, it's going to be 120 pi or 377 times 10, or about 377.0 amps per meter. Do you agree with that, everyone? Next, I needed the frequency, and because beta here is equal to 30, I know that's omega times square root of mu epsilon. Here I'm just going through what I did before. It's just doing it all over again. And I know this is equal to 2 pi f, right? And it's divided by c because square root of mu epsilon in free space is going to be 1 over c, and therefore f itself is equal to 30c over 2 pi. And what is that? I don't know.
1.4 gigahertz.
Okay, 1.4 gigahertz. And the next thing is the direction of propagation, right? And the direction of propagation, again, we look here. I know it's in the z direction, 1, plus or minus z, because that's a plus j, right? Means it's going the minus z direction. Everybody on this, make sure you know this and don't mess this up. And if you want to know how I can get that, prove it, I can take this phasor and multiply it by e to the j omega t and take the real part. When I take the real part of this, then I get the cosine of omega t plus beta z, and I know if I plot that, I'll see the wave moving in the negative z direction. Y'all with me in this class? So either way you get it, it'll show it to you. So this is going to be minus az. All right, next part.
Oh, next one. You're looking for the propagation constant. The C says a region has a property of. Yeah.
All right, for almost everybody got this right. This is just this. Literally, I took the homework problem and I changed a couple things. But maybe I didn't even change it on that first part, but it is a homework problem. So here, when they want the propagation constant, scan likely, look at this. I had one earlier. And, you know, they had a function to block scam calls, and I put that on there, and now somehow they get through. So I don't know how that's happening. Anyway, this is equal to alpha plus j beta, and this is a straight up, just stick it in and turn the crank and know what you're doing, to make sure you know what you're doing. So it's the square root of j omega times mu over sigma plus j omega epsilon, right? That's it, right? Omega is equal to 2 pi f, all right? sigma on this one, was it 5?
Yes.
Yeah, 5.
5. And then epsilon relative was 72, is that right?
Yes, sir.
All right, now the only thing you had to do was turn the crank on this. There's no tricks at all. Epsilon naught, of course, you have to know. You can use 8.854 times 10 to the minus 12 farads per meter. And mu naught, 4 pi times 10 to the minus 7th henries per meter. But it's turning the crank. And when you do this on this one, I asked for this in rectangular. Can you give me the values?
Yes, sir. 68.3 plus J, 86.6.
Y'all remember doing this, by the way? It is literally just checking boxes. I know how to do it. Turn the crank. All right, then I asked for eta, right? And eta is equal to the square root of J omega mu over sigma plus J omega epsilon. Again, same constants, you turn it in. I think this is at 37.5 degrees or something. I don't remember exactly. It's not 45, 37.5 is it?
I got 38.3.
38.3?
Yep.
Anywhere in there, and what's the magnitude? Because I don't remember.
21.45.
All right, so that was just making sure you knew how to do this properly. And these are, again, checking boxes for you. You understand the basics. Then the third problem is, are there any questions about this one? Because there's, in my opinion, this is just this straight. This is about one of the simplest tests I've ever given when I was packing some of the old ones. Because it's absolutely straightforward. There's nothing here where you had to derive anything. So the next part of this was the waveguide problem. And here, almost everybody got this right. And you got full credit for that last part. But this is the one where I had a rectangular waveguide. This is dimension A. This is just an air-filled waveguide B. And what I asked you for the first four modes of operation. So the cutoff frequencies for the MN modes are really, since it's air-filled, it's C over 2, right? Normally it's 1 over the square root of mu epsilon, but since it's air-filled, you can just put C over 2. Then it's the square root here of M over A squared plus N over B squared. And here you go through and you find out the first frequency is that you're going to get will be the TE10 frequency, right? And that has a cutoff frequency 6 point something. I forgot exactly. 6.6. 6.6.
Yeah.
456. Did you say?
I said 6.56.
56. That's fine. 6.56 gigahertz, right?
Yeah.
That's the first frequency. Then the next frequency, this is a little odd because usually it's 1020 and then 01. This next frequency is the 01, isn't it? Because you have to go through it. So it's TE01. Remember, it can't be TM because TM requires both of these to be greater than 0. So then it's the TE01, and that's 9 point, can you tell me what that is? 9.8 gigahertz. All right. Then after that, it's going to be and here you're going to get the TM or TE11. Isn't that right? And that's 10 or 11 something? 11.8 gigahertz. And finally, the last one, by the way, some people just put TE11, they put it in TM11. You got full credit for that. All right, that was 4 frequencies, even though there's a double right there. The 1-1 mode's got both E and M modes. And then finally, it's going to be what? TE2 2.0, right? And that's 13, is it?
Yes.
13 point,
I just got 13.
13.0 gigahertz. Now, these are up and on the webpage. Then, mistakenly, I put a frequency of transmission at 3 gigahertz, and I asked you to find out what mode propagated, and I didn't mean to mess that up. That should have been 6.3, which is on me. It should have been greater than cutoff for anything that propagated. Rightly so, most of you were either confused of what the world's going on, mistake, or something. So everybody got full credit for the last 2 parts. You can't lose anything on it. You got full credit. That was but that's on me because I messed that one. Now, there are people that will, I just want to say this, in case you get into some situation when you're in grad school or something. When a waveguide is driven below cutoff, there is a theoretical impedance. I just want you to know that. The impedance itself is something we don't even touch in this course because it has to do with what's called an evanescent mode, a non-propagating mode. Now, let me just mention this for completeness. I don't know where that term comes from either. So you can look it up. Evanescent means non-propagating. In a capacitor, when it stores energy, nothing propagates. You can get all that energy out. All right? When a non-propagating mode occurs, the energy, the E and H energy in the waveguide, and there will be some, you can get back down. It's not going anywhere. Do y'all follow me on that? So with evanescent mode, that's how you think about it. The actual impedance of that, you can get from those equations, but the problem is the impedance will have a J value. And I mean, that is true. It does, in fact, but there's more to that problem. And I got to tell you right now that it's beyond what we're going to cover in this class. Just remember that. It does have an impedance. In other words, if you put a voltage on a probe in a waveguide below cutoff, you're going to draw current, but you're not going to propagate anything. And the ratio of the voltage to current will be an impedance, but it'll be strictly imaginary. And I believe it's going to be a positive, or a negative J. It'll be capacitive, I believe, but I got to check that. We don't normally delve into that in an undergraduate course. All right. Finally, the last problem was the one I think everybody expected. In terms of, this is a problem that I can look through most people's work. It's absolutely clear that they had just bang, 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 bang answers. There's no scribble here, scribble there. It's pretty clear that everybody's just going through it logically. So for this one, I have 2 antennas, right? You're gonna have to help me with this one. I think I have, this one is 1.5 meters, is that right?
Yes.
All right, D equals 1.5 meters. It's an antenna. And I want to say this angle is 70 degrees, right?
Yes.
And then I have a range, is that 1,000 meters?
Yep.
And then I have a second antenna, and this is a shorty. And this one has a length of 15 centimeters, is that right?
Yes.
All right, and it does have a load attached, but for now, I'm just going to leave it like that, all right? So this is the transmitting antenna. And this is the receiving antenna. And this is at 90 degrees, too. So I think the first question I asked was, what is the actual average power density incident there, right? Isn't that right?
Mm-hmm.
All right. This is a straightforward thing. First, let's see, the wavelength or the frequency was what? 10 to the 8 hertz?
Yes.
Oh, yes.
100 megahertz, right?
Yeah.
Yes.
That's 10 to the 8. So that means the wavelength is C over F, right? And that will be 3 meters, correct? I'm just going through this, right? If it's 3 meters long, that means this is a half-wave dipole, and this is a short dipole. right?
Yep.
It's just checking boxes, going through this very logically, correct? I get down to here. Now, if I know it's a half-wave dipole, I know the average power density at any given range will be equal to the transmitted power. And I didn't put that down here, but the transmitted power on this one, I think was 80 watts, is that right?
Yes.
All right, so it's transmitted power over 4 pi r squared. Now, this is the way I always do these. I start with the isotropic power density at that point. Then I sharpen it up by the gain of the typical antenna. For this antenna, the gain is going to be 1.64. This was put down in there. And then it's going to be times the quantity cosine of pi over 2 cosine of theta over the sine of theta. And this whole thing squared. Here, theta is 70 degrees. You can convert that to radians. The trick is right here, making sure you go radians when you have the pi over 2, or you can put 90 degrees in here. Let's do everything in degrees, either one, right? And when you do that, you get the average power density. And I don't have that in front of me, but it's on one now. Can you just tell me what that is? Anyone?
8.73 microwatts per meter squared.
Milliwatts?
Microwatts.
Micro, yeah. Microwatts per meter squared. All right, what was the next part, next question?
Electric field incident on antenna 2.
Yeah. All right, so this is again, the same old stuff. So for the E field magnitude, it's going to be equal to, I know this is equal to 1/2 magnitude of E squared over eta naught, because it is free space, right? I'm trying to make sure this is as real world as possible. So here it's just the square root of 2 eta naught times average power, right? Can you tell me what that is?
0.0811, and that's micro.
0.0811.
Mm-hmm.
Go ahead.
Microvolts per meter.
Is that right, class?
I got it. 0.081 volts right here.
That should be volts. per
Volts per
meter.
meter.
It should be volts. If I gave you full credit for that, you probably shouldn't have got full credit. I didn't say that, micro. It should be volts per
It
meter.
might just be your check there. I can't quite read it.
It might be much.
I don't know.
I mean, I tried to look through them and be as fair as I can with grading. All right, that's E. What's the next thing?
It's the maximum power, the maximum possible power received by antenna 2. Yeah. No, I'm sorry.
Oh, yeah, P
P
received.
received, sorry.
Yeah, right. So now we want P received. This is the one where you take, well, this is the average power density, right? And now you need the size of it, the aperture, correct? And the aperture is going to be lambda squared over 4 pi, right? Times the gain, right?
Mm-hmm.
Since it's 90 degrees on that one, the gain is just 3/2, isn't it? There's no sine squared to be worried about, correct? Because it's 90 degrees. And the lambda you've got there is 3. When all is said and done, what do you get for this? Because you got P average right here. Stick that in, you got lambda is 3. What is it?
Got 9.38 times 10 to the negative 6 watts.
That sounds right. Okay. Then I say, I'm going to connect a resistance of 1.97 ohms, I think, right? Right? So I'm going to connect the resistance of 1.97 ohms to this thing. And I want to find the current I and the actual power that's dissipated by that load. Correct, class? And I think you remember getting problems like this. I gave you quite a few realms. So what I'm going to do is draw the equivalent circuit for that. And that means I have an open circuit voltage that I'm going to calculate in a second. Then I have to put the antenna impedance. I only said use the antenna resistance. So now we've got to calculate R rad for this. And then you put down the actual resistance I used. and I used a resistance for the load equal to 1.97 ohms. I think it's that, right? 1.97 ohms?
Yeah,
So I gotta calculate R rad for that. And when I calculate R rad, that's again 80 pi squared L over lambda squared. Here, L over lambda is 0.15 over 3. Right? And you take that and you square it, and you're going to find it's 1.97 ohms. And then you realize what I was doing. Now, with that, a lot of you realize, well, wait a second, that is the radiation resistance. That means exactly half the power is dissipated by the load, or you didn't even bother doing anything else. And half of it's just re-radiated, or you could say kind of absorbed by the internal resistance of the antenna. But for this one, some of you calculate the current first, and that's fine. I itself would just be VOC really over 2 R rad, because the actual load is R rad, and that would be the current. Can you tell me what the magnitude of that current is?
yeah, 0029.
Amps?
Yes.
Get that? Okay.
Yeah, 2.2 milliamps.
Yeah, if you want the power at the load, you could go out several ways. Power at the load is 1/2 times magnitude of that, I squared times R rad. Or you could just take P received, divide by 2. They'll give you the same answer. And is that 4.6 something? I don't remember exactly.
4.7
4.7
micro.
microwatts, and I think that's it. Is that right? Okay. Anything else on there? I think that's all, right? Okay, so that was the test, and again, the way I assembled that test is I took the homeworks, I took what we talked about in class, and I just created problems based entirely on the homework. There was nothing here that was meant to be tricky. If you look at my old test, this is probably one of the easier ones. And anything, I don't think there was anything that are throwing out. I will say one thing. A lot of people were confused about what formulas or how to apply formulas. And that's the thing, especially on the second problem. You didn't know how to find the direction of propagation. You didn't know how to find the frequency. You didn't even know how to find beta from that. So please make sure you understand the nomenclature, the terminology, because on the final exam, a lot of this gets a little more difficult because it's more complicated. There's more things going on, and you have to make sure you're clear-headed about it. There was no radar problem. I debated whether to put some of that on. I didn't try to put anything on here that was far-fetched, like a Fresnel reflection coefficient, oblique incidence, where you'd have to calculate something. I try to make it all real smooth. All right, there's nothing here that should cause anybody any trouble at all. All right, now, so where are we now? We are in EMC, and I'm going to just give you I'll say this. There's probably going to be a curve. I don't know why, but a lot of people stumbled on some of the very easy stuff. So there's probably going to be a curve, and I'll announce that next class, or I'll send you an email with it. But if you had a bad day, please be serious from here on out, because this stuff can get real hairy towards the end when we get in the microwave. I'm just telling you this honestly. This stuff was, in my opinion, this is the easier part right here. So just please be on your guard here, and don't, even if you've got a great grade, don't just, relax, because the microwave portion always gives me a little concern because it requires a clear understanding. So, you got to be very clear. There's nothing you cannot kind of understand and get through. And you can see how all this stuff kind of builds on. The propagating chapter 6, all that is necessary for everything else to really understand it. Okay. I'm not going to do a whole lot today, but I'm I'm gonna go through this. We're in the chapter on EMC. We went through wires, right? What they look like. Now, here's the three things I'm gonna cover today. I don't believe I did this. What resistors look like, what capacitors look like, and finally, the inductors look like at high frequencies. Everything that looks low frequencies looks like it's supposed to. But when we get to high frequencies, things change. So here we go. We're going to talk about what a resistor looks like at high frequencies. All right, here's how we think about this. When you think about a standard carbon resistor, you have a little tube and it's got some colored lines around it that indicate its value, right? Let's see, black, red, you go through the color code that we used to. I forgot that. I didn't even have to do that for probably 20 years. Anyway, each resistor has a value, and there's also a band on there. It'll be silver, gold, and sometimes you get like mil-spec stuff. It just tells you how close it is to that value, right? And then nowadays they print them on there for carbon resistors, but resistors can look like, they can be made from anything. And with VLSI, very large integrated circuit technology, they use lithography. They literally imprint resistors on a chip, and they don't have to be straight. Matter of fact, a resistor doesn't have to have any given shape. It just has to have a certain amount of resistance between two contact points. So don't always get hung up with it has to look like a carbon resistor, even though it's a good starting point. No matter what causes the resistance, a resistor, if it's designed to be a resistor, will always at low frequencies look like itself. That's it. If it's 20 ohms, it looks like 20 ohms at low frequency. And the lower the frequency it gets, the closer it is to a pure 20 ohms. Now, anything that resists current, and that's what resistor means, has current flowing, so there's an inductance. The leads themselves are the primary cause of inductive reactance or inductance. That's where the magnetic fields really form. So normally the leads of the wire, it's L lead, have an inductance. All right? And you can look on there in your book at this model. And here, after that, there's something else that happens. I have my book, and I'll give you a page number on this. Y'all follow me that, there's wire. The longer the wire, the more inductance. So this is on starts on 506. Then it goes to 508. He does it slightly different in the book. But I'm just going to say that this is usually lead inductance. And Whitmore's book it's got an internal inductance here. And then there's a capacitance. And I'm going to mention this because I want to be consistent with this book. Whitmore's book will have the capacitance here as some unknown capacitance. And here's why. If you think about a current flowing here, I, you're going to develop a voltage across here, plus the minus voltage. Anytime you have a difference in voltage, you have a difference, if you have some charge separation, and we quantify that with a capacitance. So if you look at his book, actually, what he does is have a little L subinternal there. Don't even bother with that. This is typically the way it's shown. Can you all see that in the book? I want to make mention of one other thing. This is just a first order shot at modeling it because, quite frankly, this capacitance could just as well be put across the lead inductance at this point. All right? This is an approximation that works a lot of times. This is basically something that works for carbon resistors. All right, so if we know that, the next thing we want to do is see what this impedance looks like right here between these two. So if we wanted to know what Zn is here, right? If you look at it at very low frequencies, right, an inductor looks like a short circuit and a capacitor looks like an open circuit. So it is just the resistance, right? But if we wanted the actual value here, we would say the Z itself would be equal to J omega or S. I'm going to use S, where S really is given as J omega or plus some sigma. We'll use the Laplace transform, or the Laplace form of this. So it's going to be S times L, lead, plus, and then these two in parallel. So it's really plus 1 over R plus, and then it would be SC, right? And in this book, it'll have it as CX. Y'all with me on this, class? Now, I can go ahead and I can simplify this a little. So I have it's equal to SL plus, I'm just going to leave it as L here because the LEAD is, there's only one inductor, plus, and then if I go ahead and I divide by C, I get plus 1 over C, 1 over RC plus S here. And when I take a look at this, and I go ahead and plot it versus magnitude of the impedance, this is Z. What you'll see is this. If this, usually what they'll do is on this axis, they'll plot the log of the frequency here. And on this axis, they'll plot either 20 times the log of the of this, but it'll be log of the magnitude of Z. That's a good way to do it. So what is the magnitude of Z? Well, this is going to be the magnitude of J omega L plus 1 over C over 1 over RC plus, and here it's going to be J omega. And I'm going to leave it like that for a reason. I know what this is going to look like ahead of time. At low frequencies, at very low frequencies, when omega is 0, it's just R. So normally what they'll do is show this come in as just the log of the magnitude of R. I know that because, frankly, if I look at that, I can tell, I can go here and I can just say is, or go even here, as S goes to 0, I get 1 over R, R plus, and 0 or just R. It starts off there. The first cut frequency right here, the first point where it starts dipping is going to be 1 over 2 pi. This frequency here will be 1 over 2 pi RC. And mark this down. This is not what we're quoting. And it will start coming down at a rate of 20 dB per decade. And then, and this is the important one, it's going to hit what's called the self-resonant frequency. Right here. And that frequency, FSR, is equal to 1 over 2 pi square root of LC. Now that's the L of the lead. Primarily, it's the lead inductance. The internal inductance of resistors usually is not a factor. I'm just level with you. All right. But when I look at this, you know, you've had resonance phenomena before, right? In your circuits courses. Remember the resonant frequency was always 1 over the square root, 1 over 2 pi square root of LC for any kind of L and C in parallel. Do you all remember that? Or series, correct, class? It is here too. When you plot these things out with MATLAB, you'll see it. It'll come down and hit a relative minimum here. And then it will start going up after that point at 20 dB per decade. Now, remember when you had Bode plots? If you had a single pole, they went down or up at 20 dB per decade, right? If you had an S squared or a double pole, it's 40, an S cubed, it's 60. Do y'all remember that class back in the days when you had circuits? All right, or I should say signals and systems. It's same here. Now, I got a question for you. How do you find this minimum here? All right. Actually, what I'm going to do is say, let's put this as 20 log. That way it'll make more sense to you. All right? Well, I know this is 20 log of R right there, right? And I know this is falling at a rate, and I'll take you through this next time in more detail, at 20 dB per decade. So I can figure out how many decades or fractional decades I've gone, and I can figure out, and I'm going to do this for you later, I can easily figure it out because I know the slope of that line to the absolute minimum. All right, or I can calculate the resonant frequency, take that resonant frequency and put it into this equation and then back it out that way. Y'all follow me? Because omega is 2 pi f. Agreed? So either way you'll get it, and I'll show you both ways, but I want to get through this part of it. So that's what a resistor looks like. Resistor at low frequencies looks like a resistor. Then there's going to be the first cut frequency here. It'll start going down to 20 dB per decade. Then it'll hit the self-resonance. Then it'll start going up to 20 dB per decade. And if you look at this thing, because I do have that wire, as frequency goes to infinity, the impedance is going off to infinity as well, because that inductance. Agreed, class? All right, that's an inductor. The next thing this bookie does, I think, is a capacitor. No, that's an inductor. All right, so we'll do the inductor. And I gotta say that this is, again, kind of, this is what an inductor looks like based on the most common kinds of inductors that you see, which are wire wound things where you have like a long rod with a bunch of wire wrapped around it. But it is not necessarily true of all things that are used for inductors. For instance, a railgun has a tremendous inductance, but this model will not work well for a railgun, I don't believe. So, what does an inductor look like? You always start with what the component looks like itself. At low frequencies, an inductor will look like an inductor. But anytime you have a lot of wire, you have resistance. So now that resistance is internal to here, and you're going to have some resistance, R. Very similar, in a sense, to a resistor. But here's the difference. Now the capacitance, when you have an inductor, if you just take a standard typical inductor like this, you get a whole lot of wraps around the core. The thing that's hard to understand is there is a capacitance between each turn that spirals around. Make sense to everybody? There will be a slight voltage difference from here to here. That voltage difference will cause a charge differential, which is given as a capacitance. So that you might say there's going to be this weird parallel kind of an inductor of capacitance across there. But that capacitance lands itself here. Now that's not exactly perfectly correct, but it's a good way to estimate what goes on. So what we do in general, they call that CX and RX, I think, in his book. The inductance is what we want, but we can't get away from the fact that there is an inherent resistance and capacitance. At low frequencies, though, you can forget about that capacitance, and that resistance is basically extremely small. So when we go ahead and we say, well, what is this, in fact, what is the impedance between these two terminals? This is in his book, right? We can do it with S. So this will have an impedance of SL. This would have an impedance of 1 over CS, right? And we can say that the actual impedance of that, and again, S is equal to sigma plus j omega, but we can look at that and say that the actual impedance Z here is going to be equal to this in parallel with this. So depending on how you want to write this, I can do it this way. 1 over this impedance, or SC, plus 1 over that impedance, which is 1 over RX plus, or just R plus SL. What I'm doing here is taking 1 over this impedance plus 1 over that impedance because they're in parallel. It's 1 over the first impedance plus 1 over the second impedance. Y'all remember doing this stuff, right? All right. That's the impedance, and we can take the magnitude of Z here, and I can do it here, I might as well. So it's 1 over magnitude of J omega C plus 1 over R plus J omega L. And if you plot that, you get this. If this is the plot, the log of F here, and on this axis, plot 20 times the log of the impedance Z, here's what actually happens. At very low frequencies, this thing's coming in at 20 dB per decade. And I'll spend more time with why it is 20 dB looking at these equations. I'm trying to get this all in here before the bell, or before this course is over. Then it's going to hit the self-resonance frequency, and that's F self-resonance. And the nice thing about the self-resonance frequency, it's the same for inductors, capacitors, or resistors. It's equal to 1 over 2 pi times square root of LC. It's always the same. And once it hits that, then it starts going down at minus 20 dB per decade. Now, it looks like the inverse of the resistor almost. There's one other thing they don't say in the book that's true. At very low frequencies, just think about this, there's a lot of long wire. At very low frequencies, that resistance will be the only thing that limits current. So even though it's small, there'll come a point where you're going to get this. And really, I'm not even going to, the way you find that out is you set this equal to this in magnitude, and you find that frequency. And you see that that's going to be 1 over 2 pi, and then it's R over L, if you take a look at that. But I don't worry about that frequency. And then it's really L over R, you can do it this way, would be that lower frequency there. You could put R on top and have R over 2 pi L, but it's usually 1 over 2 pi L over R, because L over R is the time constant for an LR circuit, and 1 over RC is the time constant for an RC circuit. Do y'all remember that? That's the only reason. And that self-resonant frequency is the thing you need. That's the main thing that they worry about. And we'll talk, if you wanted to get this peak value here, what normally you can do is just, once you have the self-resonance frequency, you stick it in there and you can solve for the value. We could talk more about that, but that's what an inductor looks like. And by the way, at low frequency, inductor just looks like a 20 dB per decade gain. We'll talk more about that in a bit. All right, that's an inductor. And in his book, he has this on page 511, right? 512. Finally, capacitors. Capacitors are the ones where you can get into some crazy models. I'm going to keep it as simple as possible and just say for most standard microcapacitors, the kind of capacitors you buy to breadboard stuff with, it's just 3 components in series. So when we have a capacitor, you always start with the element itself. That's what it looks like at low frequencies. Then, because any capacitor has wire, some like the wire, you're going to have an inductance associated with it. Really doesn't matter which way you can put this, you're going to have an L. And a lot of times he'll put an L sub lead because he'll talk about the lead inductance. And I don't know if they've taught you this in your laboratory work, but normally when you're connecting components, you want to make the leads as short as physically possible. Because leads do only one thing for you. They increase the parasitic effects of inductance, capacitance. You don't want them long. You want them as short as possible. I'm just telling you that. If you ever build stuff, remember that one lesson. And anytime you have wire, you also have a resistance. So it doesn't matter the order you put them in. Normally, whenever you see an X under there, or an E, it means this is unwanted, but it's inevitable. You can't get around it. So for this one, take a look at this. And at low frequencies, I mean, the impedance of this, as you're going to 0, is going to infinity, isn't it? Because you have a capacitor in series. At high frequencies, it's going to infinity too because of that inductance. Somewhere in the middle, when you get resonance, you have a minimum, and that would be caused by that resistance because the capacitive reactance and the inductive reactance will cancel. And what that look like if you wanted to get the Z here. In his book, he doesn't even mess with anything. He just says, well, the Z in here will just be equal to Rx, right, plus J omega L lead, and then it would be plus 1 over J omega C. He'll do it that way, and the key thing is the actual sketch here. We normally put the log of the frequency here, and on this axis, it's 20 times the log of the actual value of the magnitude of Z. And for this one, it's a capacitor. It's coming in from infinity. It's got a rate of minus 20 dB per decade here. Then it hits the self-resonance frequency, which is 1 over 2 pi square root of LC here, and that would be the L in the lead and the C. And then after that, it'll start going up at positive 20 dB per decade. Now, when I teach EMC, we go through a big breakdown of this stuff, kind of get into it, but I'm going to tell you one thing about this. All 3 of these models are general for more or less the standard off-the-shelf components that you buy. I mean, you've got the little carbon resistors, the straight wire, the wire wound inductors, and mica capacitors. They're not for high energy density capacitors or anything like that. You'll have to look and see them from a manufacturer the best way to model. And I'll tell you this much, that it's good to know some basics about this for one reason. Most of the time, this self-resonant frequency is very easy to calculate, and you don't want to operate anything near it. At least, if possible, an order of magnitude less in frequency. If you're setting up an LC circuit to resonate at a certain, say 100 megahertz, you want the self-resonance of both the inductor and the capacitor to be at least an order of magnitude below the self-resonance of either one of them, or else you're going to have problems. Because now the you could say the capacitor's inductance or the inductor's capacitance will start to affect the resonant frequency. Have you all done resonant frequency measurements yet or not? In your lab, have you looked and say, where's the resonance for this? Well, normally when you're looking at resonant effect, if it's a parallel LC circuit, you're looking for the peak value of impedance. when the current goes to a minimum or the voltage goes to maximum. Because if they're in parallel, they'll have a maximum value of impedance at resonance, right? And in series, it's a minimum value, right? So when you're looking at impedance, normally when you're tuning these things, the reason I'm mentioning this, well, I've covered what I needed to right here, but the reason I'm mentioning it, we took a ham radio when I was in college. It's one of the projects I did, I think, when I was in grad school. We took a ham radio and we turned it into we took a CB radio. We used to be able to buy these, truckers used them all the time. We'd buy them so when we're driving we could talk. And and hunters used them too, I think, a lot. So anyway, we took a CB radio and we turned it into a ham radio. Now the thing about a ham radio is, first of all, it's a lot of the emergency stuff, all the things that are emergency management's done with ham radios, and you can amplify those things. You can talk to Europe. You can talk to people in Australia. Has anybody ever used a ham radio? And they use Morse code. There's single sideband suppressed carrier. There's double sideband. There's all sorts of things. And my professor was interested in this stuff when I was doing my PhD. We had a ham shack. We even have one here, I think. They changed. You notice how it went from 2 o'clock to now it's 2:24. So anyway, this is high frequency engineering. I think we're doing a 10-meter band. So that's basically at, it's under 100 megahertz. Anyway, when we're talking about doing this, we had to take and we had to remove capacitors and put new capacitors in there at high frequency. Well, the lead length meant the world. When we went in there and when we had to do adjustments, we had capacitors we tuned. You ever see these or inductors we tuned? And we had to use dielectric rod, screwdrivers, everything. I'd even put my hand near there and the center frequency would shift. We'd watch the resonant frequency shift. It used to drive us nuts. But that's when I really developed an appreciation for very short leads and how anything, because we were not an order of magnitude less than the resonance. We were close. I mean, we had to be within 30-40% of that. And that caused us nothing but headaches. And I learned a lot about an appreciation for high frequency engineering. It's a lot more difficult than you think until you have to do it. And if any of you guys do radar work or anything where you're working up in gigahertz and you're doing these things in building, I suggest you spend a lot of time on YouTube before you do that, looking at some of the things, the pitfalls of high frequency work, because there's a lot of, anybody here going to work for any company up in Huntsville that does defense?
I'm co-oping.
With what?
Co-oping in Huntsville's a company called TSC, Technology Service Corporation.
What, I mean, is this weapon stuff?
It's radar system.
All right, radar systems are gigahertz and up.
Yeah.
All right, all the are they building real radar transmitters?
Yes.
All right, there's a whole lot of stuff that can go wrong. I'm just telling you, the high frequency, it's easy at AM, 97, 100 kilohertz, that kind of engineering is trivial. You get up to a couple of hundred, I mean, really, say 3 to 10 gigahertz, that's just X-band. It gets rough. At 33, it's a different world. So I'm telling you that ahead of time. Okay. That's about all I got for today. I wanted to get through the test and through those 3. If you got a question, hit me up afterwards. See you Friday. And no, there is no quiz Friday.